Calculate the reduction potential of zinc electrode. Zinc electrode dipped in zinc sulfate solution using standard hydrogen electrode, that is She. Now let us fabricate the cell, assuming that this is anode, because a standard hydrogen electrode, its electrode potential, that is cathode potential or reduction potential, is always 0. So in that case, let me consider zinc as undergoing oxidation, means at anode. So this is anode, this is cathode. At anode, zinc is there, zinc solid dipped in zinc 2+, is it not? And let me say this is an aqueous solution of 1 molar concentration. Then here double slash, that indicates the salt bridge, and we have the H+, that is an acid aqueous solution of 1 molar concentration, maybe HCl, etc. And that is connected to the hydrogen gas. Hydrogen is a gas, so it cannot act as a solid electrode. So in order to have some solid support, we have to introduce, that is platinum. So you can put again bar. This bar indicates the phase boundary. So platinum. So where platinum will be porous, where the hydrogen will be occupying all these holes, small holes. Okay. So platinum is a solid. It acts as an inert electrode, right? Okay. So now we have established the cell. It is called cell notation. Now we have to proceed with the calculation. So the famous equation is cell EMF, E0 cell, is equal to electrode potential. You can put electrode potential like this of right electrode minus electrode potential of left electrode. This is the basic equation. Okay. We know the value of E. What is kept at right side? She. Is it not? So we can put E0 cell is equal to, this is E and She, standard hydrogen electrode. Okay. Minus, and what about this one? This can be represented as E She itself, and this is electrode, zinc electrode potential, zinc bar zinc 2+. Okay. So E of She, standard hydrogen electrode, at the standard state is equal to 0. And for this zinc dipped in zinc 2+, we have got already the equation. Okay. So it can be obtained from the reference value, that is electrochemical series, that is the table, where you have got the reduction potential. Either it can be represented as reduction or oxidation, but our Indian convention is to maintain reduction potential. So the reduction potential of standard state zinc bar zinc 2+ is minus 0.76 volt. Now we can substitute this. Okay. So we can substitute these values. So now we have E0 cell. This is cell EMF. And what is the potential? 0, right? And what is the potential of zinc? Minus of minus 0.76. So it means 0 plus 0.76, that is equal to E naught cell is how much? 0.76 volt. So this is the cell EMF of this zinc electrode. Okay. So this is the experimental value also. This is the experimental value. So what I have calculated is cell EMF, but what is given here is reduction potential. So how we can calculate? Now I am taking the reverse. Are you able to follow? So here, as I know already from the electrochemical series, I have put this value, assuming that you do not know. But what about this? This is the experimental value. Experimentally you can get the value, you can read the value. So from this value you can obtain. Are you able to follow? Right. Now let us assume that this is the E naught cell and known value or experimental value. Take down experimental value. So what is our objective? We have to get the electrode potential of zinc. Take the reverse. Okay. So E cell, the same equation can be applied. E naught cell is equal to E naught right electrode minus E naught left electrode, right? So what is kept in the right side? On the right side we have kept E naught she, correct? And what about this? This is the electrode potential of zinc bar Zn 2 plus, and this is the experimental value. Got it? As I already mentioned, now this is the experimental value, and what was the value we got it? 0.76 volt, and this is 0, and this is zinc electrode potential. Okay, Zn 2 plus, right? Now what we can do, that is minus zinc Zn 2 plus is equal to 0.76 volt. So zinc Zn 2 plus is equal to minus 0.76 volt. Okay, so this is the way you have to calculate, and this is the reduction potential. Okay, take down, this is reduction potential. Reduction potential. And what about the oxidation potential? Take the inverse. It is the minus value. Okay, so if it is asked what is the oxidation potential, oxidation potential, so the oxidation potential of Zn bar Zn 2 plus is plus 0.76 volt. Do you understand this value? Okay. Some authors indicate reduction potential as, that is Zn 2 plus bar Zn, and this represents the reduction potential. Reduction potential. Okay. Just take the inverse, not double, single, and then E naught, if it is represented Zn 2 plus, this represents oxidation potential. But irrespective of this, we always take reduction potential only. You can either represent like this or like that, but as far as Indian standards are concerned, we consider only reduction potential. Okay, we should not get confused too much about this. Okay. If you want to be safe, very accurate, then you can put better like this, E naught, put reduction, and then zinc 2 plus bar Zn is equal to how much? 0.76 volt. Got it? If it is oxidation, means you can put the in opposite side. Okay. Now let us work out the cell reaction for this. It is now clear that oxidation, see, when a reduction potential is negative, it means what? That undergoes oxidation. Likewise we are taking, okay? If it is negative value or lower value, 0 is higher than minus, is it not? So in this case, this is minus, means lower, means just opposite. That is, it undergoes oxidation. Okay. So if it is undergoing oxidation, what is undergoing oxidation? Zinc. So at anode, take down. At anode, what occurs? Oxidation occurs. Correct. Therefore, Zn becomes Zn 2 plus 2e. Removal of electron. At cathode, reduction occurs. So in that case, what about copper? We have taken hydrogen, sorry. So here we have taken hydrogen. So H plus becomes, by adding electron, undergoes reduction, means H, but it is a diatomic molecule. So you can put 2H, 2E, right? Okay. Assuming that we do not know the value of this one. Got it? We do not know the value of this one. We are going to find out the electrode potential, standard electrode potential of zinc boron 2 plus. Okay. Let me say X. Okay, that is our objective of this equation. And what about this cathode, where reduction takes place? We know pretty well that for She it is a 0. Now what we have to do, this undergoes oxidation, this undergoes reduction. You can combine these two. So on combining, so the 2 electrons can be cancelled. Now you are able to get the cell reaction. Got it? Okay. So Zn, in fact this is oxidation potential, this is reduction potential, red. Let me take like this. Okay. Now zinc plus 2H plus gives Zn 2 plus H2. This is the cell reaction. So for which we have got the experimental value. Okay. What is the experimental value? 0.76, is it not? 76 volt. This is the experimental value. From this we can calculate X, is it not? In fact, when you put, now listen to me very carefully, in this equation you can consider E oxidation potential plus E reduction potential is equal to E cell. Got it? You can maintain this equation instead of putting minus. So in this case, what is this? X. What about this? 0. What is this? 0.76 volt. Okay. Now what is the oxidation potential? Very simple. The oxidation potential of zinc dipped in Zn 2 plus is 0.76 volt. If you want to give this value in terms of reduction, change the sign. Okay. So E red, and put, you can reverse it also. Zn 2 plus Zn is equal to minus 0.76 volt. Okay. So you have to be very clever about this. Okay. I will add one more equation. Probably that is, I would have given this equation, but I will interpret in a different way. Okay. For example, you can maintain a single equation like see this. I already suggested E naught cell is equal to E, what is that, right electrode minus E left electrode. Got it? This is irrespective of oxidation and reduction, just based on the cell notation and the position of the electrode. Since in the cell notation, listen to me very carefully, since in the cell notation we have kept the anode on the left, cathode on the right, that is why we have put anode on the left, cathode on the right. So E right minus E left. Got it? But you know very well, at anode what occurs? Oxidation occurs. Here reduction occurs. So in that case, what could be the potential? This is oxidation potential, correct? And this is reduction potential, okay? At infinite dilution rate, at infinite standard, right? So in that case, listen to me very carefully. If you want to maintain the same term, okay, you cannot use this minus plus, because here I have taken this as a reduction. Both of them are reduction. Both of them are reduction value only. But here when I use ox and reduction potential, then what is the formula? E naught cell is equal to E ox plus E red. Clear? So you should remember these two equations. You can follow any convention. Suppose if you maintain only reduction potential, then you can have this one. Okay? Got it? But how you got this minus for this? Because we already know when you maintain this as a reduction potential, when you take the oxidation, it will have the reverse sign, is it not? And that is why I put R, that is minus here, but here plus. Okay? Now let me write once again the E cell value. The E cell value of zinc electrode. Now this is, what is the oxidation potential? We have just now discussed. The oxidation potential is how much? So here I have given as oxidation potential 0.76. So according to this equation, 0.76, correct? As reduction potential 0, correct? So the result is a 0.76, okay? If you want to maintain this equation, now listen to me, E naught cell is equal to, you have to use only reduction in both cases. So if it is oxidation, I have to change the sign, is it not? Are you able to follow? Okay. Is it clear? So E right minus E left means on the left side I have put the oxidation, is it not? And this one is 0 minus of minus 0.76. Now you get it, 0.76 only, okay, right? In certain books they follow this method, in certain books they follow this method, but in my opinion, as far as reactions are concerned, you can add just like that, but you have to be very clever in that is reproducing the value. But here when you calculate by scientific, the cell notation, then you can follow this simple procedure. Got it? But you cannot follow this one also, but you should remember in terms of reduction potential only. So accordingly you have to change the sign. So instead of confusing yourself too much, my suggestion is maintain this formula for calculating the cell EMF from the cell notation. And from the cell reaction means you can adopt this equation. This is the best way, right?